The United Nations has laid out two massive scientific mandates: the Decade of Ocean Science and the Decade of Action for Cryospheric Sciences. Achieving these global goals presents a significant physical paradox. To protect the Earth's most critical ecosystems, humans have to act in environments where survival is virtually impossible. We have to collect data beneath miles of polar sea ice, intervene in deep water high current zones, and maintain remote offshore energy sites. Because we cannot send humans into these extremes, we rely on marine robotics, remotely operated vehicles, and autonomous floats to act as our physical proxies. To understand how this translation from policy to hardware occurs, we can look at the request for proposals issued for the 2026 MATE ROV Ranger competition. We are going to deconstruct how macro-level UN directives are broken down into 4 specific, localized engineering constraints. The survival of these mandates rests on hyper-specific mechanical and systems engineering solutions. The first major UN objective is to protect deep-sea biodiversity and restore delicate marine ecosystems. This chart shows the Funk Island Deep Marine Refuge, located off the eastern coast of Newfoundland. This is a primary testing ground for these observation efforts. Recently, researchers operating in this sector discovered a densely populated, rare, cold-water soft coral garden. To document a habitat like this without physically destroying it, an ROV must carefully operate inside the severe, sweeping currents that naturally run along the seafloor ridge. The mission demands the ROV use a specific data acquisition method known as photogrammetry. By systematically capturing overlapping two-dimensional photographs, the ROV provides the exact data points required for software to stitch together an accurate, measurable three-dimensional topographic model. To execute this, the ROV pilot must maintain strict spatial awareness, holding precise vehicle positioning and flying linear transects directly against the water flow. Mapping these gardens in 3 dimensions requires robotic platforms stable enough to operate in heavy flow, turning discovery into measurable, long-term monitoring data. The next UN objective mandates the expansion of the Global Ocean Observing System through persistent coastal monitoring initiatives. We can see this in action through the Smart Atlantic Alliance, specifically their subsea observatory linked via fiber optic cable near the Holyrood Marine Base. One of the immediate biological challenges in this observation sector is tracking invasive species, like the European green crab, without having to rely on physical capture traps. The hardware solution the ROV must deploy is an environmental DNA, or eDNA sensor, which sequences cellular fragments shed directly into the water column. In the exact same region, the ROV is required to execute heavy physical interventions, such as protecting the critically endangered North Atlantic right whale from entanglement in vertical fishing lines. The mechanical solution to this hazard is a bottom-stowed trap using a ropeless acoustic release. The ROV simulates the precise acoustic signal to trigger the buoy release, then executes a high-torque recovery to haul the trap to the surface. Modern underwater observation networks force vehicle design into 2 opposing directions on a single dive. The ROV must operate as a delicate biochemical sampling tool and a heavy lift recovery crane. Scaling up ocean-based solutions to climate change requires rethinking offshore energy infrastructure to create a sustainable ocean economy. Equinor's Hywind Tampen is the first floating wind farm engineered to power offshore oil and gas installations with renewable electricity. Mooring these massive floating structures in deep water introduces a difficult subsea construction challenge. Industrial anchors, known as micropiles, must be driven directly into the seafloor. The drilling process required to seat these micropiles generates intense acoustic pollution that actively harms surrounding marine life. To meet environmental regulations, contractors utilize a mitigation technology known as a bubble curtain. Compressed air is pumped into a ring-shaped hose surrounding the drill site. The resulting vertical wall of bubbles physically absorbs and dampens the sound waves radiating from the machinery. This creates a complex operational sequence for the ROV. It must lay the bubble curtain array, install the micropile anchor, and then precisely route heavy power cables between the wind farm's subsea station and the oil platform's input port. Achieving a sustainable hybrid energy grid relies on subsea robots capable of building heavy infrastructure while simultaneously deploying the systems required to mitigate the environmental impact of their own construction. Our final mandate focuses on unlocking climate solutions through continuous observation of the cryosphere, the Earth's frozen regions. This map details the deployment of the GOBGC project, a global network of 500 autonomous profiling floats designed to track long-term ocean chemistry. In polar regions, these robots face a fatal mechanical threat. If a float ascends beneath shifting sea ice, it will be crushed or trapped. To survive, the system requires a software adaptation, ice avoidance capabilities driven entirely by sensor data, without any human input. As the float rises, sensors measure water temperature. If data indicates an ice canopy overhead, the float aborts its ascent and dives. Unable to transmit underwater, it locks collected data into internal storage across multiple profiles until it detects open water. The Mate Ranger competition simulates this constraint directly. Teams must engineer a float that ascends to a specific depth, holds autonomously under the ice, and delays data until recovered. Operating in the cryosphere demands an integration of physical durability and autonomous logic. The vehicle must be robust enough to survive the cold, but intelligent enough to avoid the ice altogether. When we pull back from these individual operational tasks, we have to look at the remotely operated vehicle as a complete, unified system. Historically, an ROV was effectively a waterproof camera attached to a joystick. The mandates required by the 2026 directives demand something more complex. Today's vehicle is a massive, multidisciplinary systems engineering challenge. On a single deployment, the machine is expected to act as a topographical surveyor, a genetic chemist, an offshore construction worker, and an algorithmic decision-maker. These intense hardware constraints transfer directly onto the human operators. Designing, budgeting, and piloting these machines requires a vast overlapping matrix of technical competencies and organizational skills. The engineering constraints of the Ranger class force teams to develop the technical and operational fluencies required to execute environmental policy on a global scale. The United Nations mandates have provided the global objectives required to protect the ocean and the cryosphere. It is the next generation of engineers that will actually push the robotic performance to achieve them.